All right, let's jump in. I want to talk first about preferences, and in particular, I want to talk about the utility function and indifference curves. So let's jump in. First, a little overview of consumer theory. We really have two major building blocks toward demand, which is going to be the outcome of this whole theory. We'll start with preferences. The idea is kind of simple. More is better, that is, people would prefer more of stuff to less of stuff, but people get sick of stuff when they get a lot of it. That's in some sense the whole idea that gets this process going. Later on in this module, not in today's or not in this video, but a little bit later, we'll introduce budget constraints, which just really say that you can't spend what you don't have. When you put those two things together, then we'll be able to derive the whole theory of the consumer and the demand curve. But one thing at a time. So what I want to do is build a structure for talking about preferences and the utility function and indifference curves. And so our first tool here is what we call commodity space. So our goal is to be able to describe the level of satisfaction that the consumer gets from each bundle. But first, to do that, we need to be able to just describe bundles. We're going to work with two good bundles, just because we like to make pictures on paper, and paper's two-dimensional. We'll characterize a bundle as an ordered pair, open parenthesis x comma y, where x is the number of some good, let's say apples, and y is the number of some other good, say oranges. So, for example, if we saw the ordered pair 5, 4, what that would mean is 5 apples and 4 oranges. And the point is, or a point to make, is that you can represent a bundle as a point in a two-dimensional commodity space. So that's what commodity space is, and let's illustrate it. So here we have on the horizontal axis x, the number of apples. On the vertical axis y, we have y, the number of oranges. And so 5 apples and 4 oranges in commodity space is, well, 1, 2, 3, 4, 5 along the x-axis, 1, 2, 3, 4 along the y-axis. And there's the point associated with those, and indeed, that's the bundle, 5, 4. Now that we've described just the amount of stuff that the person has, let's move toward describing the satisfaction associated with the bundle. And so for this, we'll use something called the utility function. What we're looking for here is a mathematical way to represent preferences. And the utility function, to define it, it's a function that evaluates a bundle and then spits out a number that we call utility. And you can just think of it as the satisfaction associated with the bundle. The way we'll denote the function, it's u of x and y, so here it is. And what it says is how much utility does the individual get from consuming some particular bundle, let's say 5 apples and 4 oranges. Now, one way to talk about the utility function, the natural way to introduce it, is to talk about the properties of utility. And so there are going to be 3. The first of these properties is the idea that more is better. Okay? More is better. Now, to illustrate the more is better idea in commodity space, let's start with some particular bundle called A. And it's the bundle we've been talking about, 5 apples, 4 oranges. The more is better idea helps us divide this region into a couple of kind of subregions. So let's start from A, because more is better than having either more of good X, going this way, or more of good Y, which would be going this way, or both, which would be going this way. That's going to make the consumer better off, meaning he or she would have higher utility. Well, why? Because more is better, and if I have more stuff at a point like this than I had at a point like this, then I'm better off at a point like this than at a point like this. Similarly, starting from a point like A and reducing the amount of good X this way or this way, well, having less of X or Y or less of both would make the consumer worse off. And so this region here in this quadrant has lower utility than point A, whereas this region up here has higher utility than point A. Now, these other regions with the question marks in them, more X, for example, with less Y, so we're going this way in X, but having less Y, so we're in here somewhere, or vice versa, more of good Y and less of good x, putting us in this region, well, that's a question mark. So some consumers would be better off at any particular point there relative to A. Others would not. Okay? But this nevertheless is a clue already about what something that's coming later, the indifference curve, is going to look like. Well, we'll get there. The second property of utility and utility functions is something we call completeness. The idea here is just that the consumer knows what he or she likes and can therefore rank order all bundles. So for example, now we have two bundles in here. Bundle A is 5 apples and 4 oranges. Bundle B is 4 apples and 6 oranges. So the consumer can determine whether, for him or her, it's true that the utility of 5, 4, that is the utility of point A, is bigger than the utility of 4, 6, or the utility of 5 and 4 is less than the utility of 4 and 6, or that the utility of 5 and 4 equals the utility of 4 and 6, in which case the individual would be indifferent between them. But again, all we're trying to say is, give me a couple of points in commodity space, and the individual can tell you which one he or she prefers. That's what the utility function is going to spit out. If the utility function spits out a higher number for one, then that one is preferred to the other one. The third property we call transitivity. So transitivity is kind of a property of consistency. The idea is this, in the box. If the consumer prefers bundle A to B and prefers bundle B to C, then the consumer must also prefer A to C. Now, it's just kind of a property of rational consumers with stable preferences, and I think most grown-up people tend to obey this property. But the idea is now we have 3 points to consider, and so this story about A, B, and C could be a story about these 3 points in this diagram. Now let's get down to a mathematical example that we tend to use a lot in this class. And so this now is the utility function u of x, y equals the product x times y. This is almost the simplest utility function we can use that gets our point across. And since we are going to be using it a lot, let's just start in with that. So what I've done in this slide is to depict three different bundles. There's bundle A, which we've seen a lot now, with 5 apples and 4 oranges. There's bundle B with 4 apples and 6 oranges. And then there's this bundle I've called double A, which just doubles the quantity of x and the quantity of y. So instead of 5 apples, it has 10 apples. And instead of 4 oranges, it has 8. So it's got double what's in bundle A. Up in the table, what we've done then is depict these bundles in terms of their quantity of good x, the apples, quantity of good y, but now we've added another column, which is the utility associated with the bundle. So bundle A, we evaluate by x times y, and x is 5, y is 4, so x times y is 20. Bundle B has 4 and 6, the product of those two is 24, and double A, the last bundle, has 10 and 8, and 10 times 8 is 80. So all we've done in this diagram so far is just depict some points in commodity space and then calculate the utility associated with those points given this particular utility function. Let's make a few comments about what's going on in that diagram. This individual, who again is described by this particular utility function, u equals x times y, this person prefers B to A. Now how do we know that? Well, we know that because the utility associated with bundle B, which is the utility of 4, 6, equals 4 times 6, or 24, whereas the utility associated with bundle A, which is the utility of the bundle 5, 4, just equals 20. And of course, because 24 is bigger than 20, the utility of B is bigger than the utility of A, or just to say it in kind of human terms, this person prefers B to A. So we could do that for any 2 points, but there it is for B and A. Second point I want to make is that a particular utility function, and here we've written down u equals x times y, a particular function just describes an individual. So although this is a very parsimonious characterization of behavior, I don't mean to suggest that everyone has the same utility function. In fact, if you think about it, you and I probably like apples and oranges to different extents, and so you and I would have different utility functions, and we could write down different mathematical functions that would characterize your and my utility. And we'll talk a little bit about that later, but by and large, for the purpose of working problems, it's just easy to work with u equals x times y. But let's not think, therefore, that we're forgetting that there's heterogeneity in the world. No, we understand that. Okay, so far, finally, the last point I want to make on this slide, so far all we have is a characterization of preferences. That is, how much satisfaction does this individual get from any particular bundle? That's not yet a description or a theory that actually describes which choices people make. To get to that, we're going to have to bring in budget constraints, which characterize how much we can afford. All right, let's move along. Let's offer this definition of what's called indifference curves. Now this is another way to use the utility function, and it turns out this will be really handy for showing what the consumer actually chooses. What is an indifference curve? Well, the definition is that it's a locus of consumption bundles yielding equal utility. So it's a bunch of x's and y's, right? It's all the combinations of x and y such that u of x times y equals some constant level of utility. All of which is another way of saying that the consumer is indifferent among the bundles on the same indifference curve, where again bundles are just particular values of x and y, particular amounts of apples and oranges. Now what would these things look like? And what I want to illustrate here is indifference curves for different levels of utility. So let's have three levels of utility. U2, which is bigger than U1, which is bigger than U0. And so what we would see in any diagram is that U1 is sort of to the northeast of U0, and U2 is to the northeast of U1. Another point that's important to make, and it's implicit in what we've said before, is that as long as both goods increase utility, which was our more is better assumption a couple of slides back, that means the indifference curves have to slope downward. And of course, that's very intuitive. If I like apples and oranges, then if I were to get more apples, in order to stay as happy as I was before, I'd have to give up some oranges to remain at that same level of utility. So indifference curves need to slope downward. Now how about an example? So again, we'll use our function u equals x times y, but now we'll consider the level of utility where where x times y equals 9. What's the resulting indifference curve? Well, if u equals 9, then we can just rewrite that as y equals 9 over x, where again x times y equals 9. So that just means dividing both sides by x, we get y equals 9 over x. And so over in this table, we've just picked a couple of, or I should say more than a couple, but a bunch of points along this indifference curve where the product of y and x is 9. So for example, excuse me, that's true when x is 1 and y is 9, because 1 times 9 is 9. If x is 2, then having a y of 4.5 results in 2 times 0.5, or 9, 4.5 rather. If x is 3 and y is 3, then we're at 9. Now, of course, we could go on, but the point is, any collection of x and y that satisfies x times y equals 9 is going to be a point along this indifference curve. And these points along this blue indifference curve are exactly that. So this is the indifference curve for x, y equals 9, or you could just say for u equals 9. One other point I should probably mention now is that a lot of times in this class, since we're actually using math, we'll consider examples where the numbers of apples and oranges, or whatever the good is, could be actually fractional. When we're thinking about things that only can come as integers, we'll mention that. But since we're working with math, and there are particular values where you get integers like 199 and 339 and 919. But for many of these, if x is an integer, y is going to turn out to be a fraction or a decimal, and that's okay in this class. Let's go on. Now let's illustrate two different utility levels, again with a specific function and specific numbers. So we're again thinking about u equals x times y as the function that underlies this picture, but you can certainly see in this diagram that the higher level of utility, the red line, is to the northeast of the lower level of utility, the blue line. Okay? All right. I want to introduce another term that's related to the utility function and the indifference curve. It's a term called the MRS. So what is that? It's the marginal rate of substitution, but even that's just a word. What is it actually? It's minus the slope of the indifference curve. So here we have an indifference curve, and we've seen some of those before in this section, in this little module. So at any point along this indifference curve, we could say, well, what's the slope at that point? What's the slope? We draw a tangent line at that point. That would be the slope. Well, so the slope is itself going to be negative because the indifference curve is downward sloping. Just as a matter of convention, we want the MRS to be a positive number, so we say minus the slope of the indifference curve is what the MRS is. But that's all so far just very definitional. So what is it intuitively? Well, the MRS shows the individual's willingness to trade off the two goods. So, for example, at a point like this, which is now covered with red stuff, the slope is very steep, meaning it looks like the individual would be willing to give up a lot of oranges to get a little bit of apples. You know, whereas elsewhere on this particular indifference curve, the slope changes, and so the willingness to trade off one for the other will change. Now, we'll talk about that idea more later, but right now what I want you to get is simply the idea that the slope of the indifference curve and minus the slope of the indifference curve both just show the willingness of the individual to trade off one good for the other. It's interesting to think this through, but a particular individual's indifference curves, for example, my indifference curves, cannot cross. Okay, now it's kind of fun to think about this. So let's draw an example. So here we have an example with books on this axis and video games on this axis. And by the way, in this example, it really doesn't matter what we put on the axes. But we have two indifference curves. One called U1, which is the green one, and one called U2, which is, I guess, the orange one. Now we've labeled 3 points. A is the point where the two indifference curves cross. B is a point on U2, and C is a point on U1. Now what are we doing here? We're playing this game. So my assertion is that indifference curves cannot cross. To show that that's true, what I want to do is suppose they did cross, and then see that this leads to a contradiction, which then would demonstrate to us that we cannot have them crossing. So that's what we're doing. We're supposing that they did cross, and then seeing where that leads us. So if they did cross, suppose they did, it says here, if they did, then the utility of point A would be equal to the utility of point B. Well, why is that? Because they're both on utility indifference curve U2. They both have level of utility U2. But it would also be true that the utility of A equals the utility of C because they're both on indifference curve U1. But that implies that the utility of B equals the utility of C. Because if the utility of C equals A and the utility of B equals the utility of A, the utility of C has to equal the utility of B. But hang on there, more is better clearly shows us that C has higher utility than B. Now how do I know that? Just look in the diagram. Relative to point B, C has more of both things. So there's no way that C and B could have the same level of utility. All of which is a long way to say that indifference curves cannot cross for an individual, because if they did, we'd be led to contradictions like this. Before we leave this slide, though, I want to make one point. I think this should be clear from stuff we've said already, but let me say it again. Although my own indifference curves cannot cross each other, mine and yours can certainly cross. You and I might have different willingnesses, and surely we do have different willingnesses to trade off apples for oranges, or Brussels sprouts for oranges, or whatever. All right. We've gotten partway into utility theory, and it's time to take stock and take some takeaways. First point, a bundle, the thing we've called a bundle, is a point in commodity space. And it's just how much of this good, how much of that good the individual has. Second, the utility function shows the level of satisfaction associated with any bundle. And in this commodity space, utility will be increasing to the northeast. That is, as we go that way, more stuff. A third point is that the indifference curve is a locus of bundles yielding equal satisfaction. And if more is better for both goods, then it has to be downward sloping. Last point is the MRS. It's just something we're going to define as minus the slope of the indifference curve. But intuitively, it shows the consumer's willingness to trade off good X for good Y.